And now I want to, uh, once you've designed your model, you want to find, or one important problem is finding the most probable state in this model. And so there are a couple of inference problems, and one important one is finding the maximum a posteriori estimate. This is the one I want to talk about now. There's also a problem of finding the marginals, or sometimes you even need to estimate the partition function. But here I want to talk about the map problem, so finding the maximum a posteriori value. So in the following, so as a header, let's call this maximum a posteriori estimation for discrete valued MRFs via ILP, where ILP is integer linear programming. Without loss of generality, we will consider only pairwise MRFs. Because something I alluded to earlier today in a paper by Yedidia and others, it was shown that you can actually convert any higher order factor graph into pairwise MRF. So if you look this paper up, there is a figure 8 that I will reproduce here, which shows a ternary factor and a couple of unary factors, and which explains how you can turn this into a pairwise MRF by replacing each factor with a new random variable, and then you need a couple of observed nodes in addition. And if you want to know more about this reduction or construction, then have a look at this paper. So I write the probability of a set of hidden states as 1 over the partition function. And then because it's an MRF, so I have a graph of script V vertices connected by script E edges, and have a product over all vertices. Psi I is again my potential associated with the ith site, and then have a product over all pairs of vertices that are in my edge set. And if I take the log of this, or if I'm interested in the map solution, so if I'm interested in this solution X, which maximizes this, then I don't need the partition function, which is very helpful. And I can say that I want to minimize over the following sum. That's, of course, something that you've seen many times now. And we have called this the energy as a function of x. Now comes something new, namely a funny encoding of this equation. So I can rewrite this energy as follows. By introducing a set of indicator variables. So I'm using script L to indicate the label set. So the set of labels that each random variable in this categorical distribution can take. And here are my indicator variables. I use subscript I to indicate its location in the image, and I use K to index the label. And I multiply this with the single side potential. Excuse me, this should be K. And so this is the unary term with Qi of K being 0 or 1. So I is, what is this called? A function which is 1 if its argument is true. The characteristic function, thanks. What's the other name of this? It's not a rhetoric question. Sorry? No, it's not. Anyway, there's another name for it, which I've forgotten now. It's the characteristic function. Yeah. So let's say I of a true argument is 1 and I of a false argument is 0. Okay. So you see that I've introduced a whole vector of these new indicator variables for just the ith site. But this was just for the unary terms. And I hope that you agree that the value of this will be the same as for the unary term above. Do you agree? Yeah. So I'm setting Qi to 1 if my hidden state X at the site I assumes label number K. So if so, I'm multiplying with psi ik. This is just psi ik itself. And otherwise, I'm having a 0 here. Okay, so this is just a complicated way of writing the first term here. I should also have written it here. So you see Qi depends on K and on Xi. So the first argument here is the pixel index. And the second argument is the label index. If I have a binary Markov random field, then K would be in the set 0 or 1. But if I have a categorical Markov random field where the label set can be apples, pears, and bears, and others, then for each category, if I have 10 or if I have 21 categories like in the MSRC, then K can take values between 1 and 21. Okay, so if I want to express it in numbers, I could say this is K goes from 1 to the size of the label set. It's maybe a better way of writing it. Okay, this was for the single side term, and now we still need something for the pairwise term. So there is now we have a summation over all pairs I and j in the edge set. And then we have a summation over the labels that I could have at pixel number I, and over the labels at pixel number j. And I now have a whole table of indicator variables, or you can think of it as a longer vector, which again multiplies the term that I really want to have. So in this time, Qij of Kl and Xi and Xj is the indicator function. This is the word I was looking for, of the following statement: Xi equals K and Xj equals L. So I have an overcomplete or redundant representation in terms of these indicator variables, and they simply pick out the term which is true or which holds for a particular labeling. So let me zoom out a little. The thing up there was the energy of X, I had said, and the whole thing that we have now, so this taken together, is still just the energy of X, with Q being a deterministic function of X. So we have this function here and this function there. These are deterministic functions. Now I could turn the argument around, and I could want to write an energy which is a function of Q, the indicator variables, rather than X. So I can turn this into a function of Q rather than X. And then I could say that, I have a new rule now which says that Xi is a function of Q. So you see these indicator variables are now 0 or 1. And if exactly one of them is 1, then Xi will take the value K. And already this formula here tells me that if I want to write this as a function of Q, I will need consistency constraints. So we need to think of everything that could possibly go wrong if we now specify the Q's rather than the X's. So if you specify the indicator variables rather than the original random variables. So, for example, I need the constraint that just one of the variables at site I, just one of the indicator variables, should be switched on. We already know that they are binary, so I will have a constraint that Qi of K is either 0 or 1. And then here I have an additional constraint that if I sum over all labels K, exactly one of them should be switched on. So what have we done so far? We started off this function e of x that you know very well already, and we've written it in a more complicated form, introducing these indicator variables, which are either 0 or 1. And that is for a reason, of course, because I want to find a formulation that looks like a well-known optimization problem. And here it is. So I can write this as an integer linear program, or ILP for short. And I'm going to call this equation 1. It's the only equation with a number of today, because I want to refer to it. So I want to minimize over all my indicator variables q, which I here simply collectively call q. Then copying down a little from above. Here I no longer have my argument x. So I sum over all neighbors j of a random variable I. And I sum over the labels k that I can have at position I and over the labels L that I can have at position j. And I multiply it with a potential function psi. And now come the consistency constraints. So I want to minimize this such that my single side indicator variables are either 0 or 1. And this must hold for all vertices, and it must hold for all labels. So I assume that this set of labels is now just a set of integer numbers, or encoded by integer numbers. Similarly, I want the indicator variables for my pairwise interactions to also be binary. And now come the more interesting ones. I want just one of the indicator variables associated with a single side to be switched on. And now comes a more interesting one. That's the one that needs most looking at. I don't like this picture yet. So let's say this is the vector qi of k, where here k was 1, k was 2, k was 3. And similarly, this is qj of k. So I'm indicating, for example, that at pixel number I, that I'm in state 2, and at pixel number j, why not? Let's also say that I'm in state number 2, and encoded here is qij of k and l. A solution that would be taboo would, for example, be the one here. Can you argue why? Yeah, exactly. So qij, this is an indicator variable. I can write this as qi of k times qj of l. This is a condition that should hold, and it's violated here. Okay, so this line tells me that my 1 should be somewhere in this line or row. This one tells me it should be in that column, but the 1 is elsewhere. So the solution is taboo. Now, what you have just said is correct. This is a condition, the condition that you've given, which I could include as additional constraint in my optimization problem, but it is a condition which is quadratic in the variables. And I want to end up with a formulation that is linear in the variables, both in the objective and in the constraints, simply because this is what defines an integer linear program, and there is a huge amount of work has gone into the optimization of such integer linear programs. So we want to be able to use existing proofs, existing code, and so on. This is why I'm looking for an integer linear formulation. And this is why I'm using this condition here, which says that whatever the pixels I and j, as long as they're in the set of edges E, are, so this would be here, this would hold for all I, which are neighbors of j, or for all pairs of ij in the set of edges. And it also holds, or should hold, for all k. So it says if I sum across one row of this table, then I obtain a vector, and this should match the vector of the unaries here. And if I sum across one column, then the same should hold. And by the way, I don't need I think that means I don't need to write down this constraint explicitly. I could also just say that all elements of this table must be larger than 0. That should also be enough. So there is a large set of, or you can formulate the same problem in a valid way, in many different ways. Valid meaning that solving this amounts to solving the original map problem that we started out with. So solving this map problem is equivalent to finding the solution to this problem 1 here, and then afterwards translating this solution back into the state of my hidden variables by using the formula that I've just put a box around. So I have many comments to make on this. Before I do that, are you happy with this? equivalence and with this equation. So I have many comments, perhaps they will further clarify the matter. My first comment is that these numbers psi I of k and psi ij of kl, well, they are just that. They are just numbers, and numbers that can be pre-computed. So in terms of the optimization problem, I can just think of them as constants. Next, my objective. Objective is the thing that I want to minimize. So this here is my objective. The objective is linear in Q, where I define Q to be the collection of all these univariate Qi's and all these bivariate Qij's, you know, for all I in V and Ij in the H set. So the objective is linear in Q, and so are the constraints. With the exception of the integrality constraint. So with the exception of the constraint that the solutions must be binary. So overall, what has happened is we started out with a discrete, or with a function of discrete input that can be highly nonlinear, and we have linearized it. And we paid a price for this. So this linearization came at the expense of inflating its dimensionality. Because I have introduced for each factor, a for each pairwise factor, I've introduced a set of variables indexed by I and j. Okay, but now overall is just linear in these new variables q. So what I mean by inflating the dimensionality, let's say originally we had x, which was in 2 to the power of number of vertices, or not 2. If we have a larger set of labels, then it was the number of labels that we have to the power of number of vertices. And now this q, this is a binary, so it's 2 to the power of, and I have a number of vertices times number of label plus number of pairwise constraints. So this is the size of the edge set times the number of labels squared what, state or dimensions? Hold on. These are, I've already given I've already given the states here. So those are the number of states. And the dimensionality would just be the exponent. So here I had one state for each vertex, and here in a new case I will have one state for each of these indicator variables. So such a problem, which is linear in the constraints and linear in the objective, if it was just that, would be called a linear program, but because we also have the integrality constraints, it's called an integer linear program. And such integer linear programs can be written as follows: as a maximization over some vector of rewards C, and then Q is a vector of variables over which we want to optimize. And this is subject to the constraints that AQ should be no more than B. The elements of Q should be non-negative, and the elements of Q should be integer. And as a minor comment, we had in the constraints not inequality, but we had equality constraints. So if I scroll back up, you see I had an equality constraint here and an equality constraint there, rather than an inequality constraint. But equality constraints you can always express through inequalities. So if I want to say that, if I want to say instead that I want to enforce that, so there's a comment here, if I want to enforce that BQ should be D, or I can use the same, well, okay, anyway, let's say D, then I can write this as BQ should be no less than D. Let me say no more than D, and minus BQ should be no more than minus D, which is the same as saying that BQ should be larger than D. And now these two taken here together, I can rewrite. What is too much? No, I think I need two minuses, so I multiply. Yeah, so I take this equation here and I multiply it with -1 on the left-hand side and on the right-hand side, and it gives me that one there. And now, like you observed, this only holds if there is equality. So this amounts to saying that BQ should be D. Oh, A is, so this is just, so the question is, what is A? This is just the generic form of an integer linear program. And now we can relate it to our case. So you ask, what is A? Let me scroll back up. So here we have, so to remind us, we have the constraint that A times Q should be, or should be no less than, let me write equality here, for the reason that I've just given. I can write equality here. And so each row of A tells me that one particular linear combination of the elements in Q should take one particular value. So I can say that this equation here corresponds to one row of this linear system of equations for a given value of I. but now this is for all I in the vertex set, so this will be a large number of rows. And then here there are further number of rows, there are further rows that I can add to this system of equations, because I define Q to be the collection of these and of those terms, all appended to each other. Okay? All right, so here's the generic form of an integer linear program. And this is just a reformulation of our original problem. So you ask, by just reformulating, have we gained anything? So so this is again the generic form of an ILP. In our particular case, yeah, it can be any integer. Yeah. Well, any non-negative integer. Yeah. For example, so how do we restrain it to just binary ones? For example, by using this form and saying it must not be larger than 1. Yeah. So but thanks for the question anyway, because they help clarifying for everyone, I think. Yeah. So by identifying the maximum a posteriori problem of a binary, possibly multinomial, using this. So by identifying the maximum a posteriori solution of a binary multinomial MRF with an ILP, the crucial question is, have we won anything? Now, your hero is never going to die at the beginning of a movie, at least not of a straightforward one. So of course I wouldn't have talked about it if there was not at least a partial yes to this answer. But it's a yes and no. So no, because solving an ILP is NP hard in general. And incidentally, many hard problems can be rewritten or can be expressed as integer linear programs. So we've taken an NP hard problem and we've rewritten it as solution of another NP hard problem. So that's the no part of the answer. But there's also a yes part of the answer, which is that pretty sophisticated solvers are available. And at least for small instances, we can just throw it into one of these solvers. In addition, there is extensive literature, I'm shortening this here, plus great literature, which actually comes to great extent from econometrics. So the OR or operations research people have looked into many of these problems before image processing people did, and the latter have a lot to learn from the former. So it was literally, the ideas from operations research from the 60s that were started to being used in the 90s and in the 2000s in image processing, which is not just because image processing people are dumb, but also because operations research people sometimes deal with 10 instances in a problem or with 20, placement of factories or so. Yeah? So you have how many factories are you going to build? Maybe 2 or 3. And how many customers you have. If you don't sell to end customers, a limited number. So they had pretty small instances Whereas in image processing, we have millions of pixels, and if we make life a bit easier and build super pixels, we still have hundreds of them. So computers also had to become fast enough for us to be able to use these algorithms. But at least small instances we can directly plug into such existing software. And to give you a few examples for such solvers, sorry for my poor writing, solvers are on the commercial side. There's Cplex and Gurobi and Express and others. And on the open source side, there is LPsolve and GLPK and others. And unfortunately, there is a factor of 20 or so in the running times, well, in favor of the commercial ones. On the good side, some of these commercial programs allow free academic use. Okay, so it's so nice to be an academic sometimes. Yeah. Okay, so we can use the solvers, and also, still on the yes side, if we use one of these, we can learn something, because if we solve a problem to global optimality and this globally optimal solution is still unsatisfactory, then we know that our error was lying in the modeling or in the specification of our Markov random field and not in the optimization. So let's say we can, by optimizing globally or by optimizing to global optimality, we can decide who's to blame if things don't come out as hoped. If it was the designer, that's us, or if it was the optimization. And well, if we've sold to global optimality, then we know it's not the optimization. So that's on the good side. Now, what does this buy us? I have an image here from a paper published in 2006 by Janova, Meltzer, and Weiss. And they picked images of a varying size and showed that a couple of commercial solvers within a given budget of RAM and compute time could solve problems on images up to size 50 by 50. Unfortunately, your smartphone cameras have, a million by a million pixels. So there's if you go by that, there's a long way to go. However, fortunately, we have smart people like sitting at, down this corridor. Here is an upcoming paper of your Kappes and colleagues. It will be published in a few weeks. And they use commercial solvers, but they help them on their way. And they do that as follows. There are a couple of methods like QPBO that give you so-called partially optimal results. So if you look closely, you see a couple of black dots here, and QPBO could give the definite answer for these pixels. So QPBO tells you that for these pixels we have a labeling which is either 0 or 1, and for those pixels we know that these labels are also part of the globally optimal solution. Whatever the globally optimal solution is, at the marked pixels here we already know those values. So, these are quite literally, these are zeros or ones. Perhaps I should, have given a concrete example here. So let's say we know that in the globally optimal solution, here the optimum label is 0, and there it's 1, and there it's 0. But we have a question mark, or rather in QPB, we have a question mark at the other pixels. So what your Kappes and colleagues do is that they first leave out those parts for which we have a solution, because we can condition on them. And that's what you see in this image here. So the parts where a solution exists have been eliminated from the graph, and then these factors had been modified. So this used to be a binary factor, but so a function of two variables. But one of the two variables has a known value, so it becomes a function of just one variable. And you see it has changed its color here. Okay, so these factors had to be modified, but they are still ordinary factors in a factor graph. And now look what we have. We have now two disjunct problems, or two connected components in this graph. And you would hope that a great general purpose integer linear program solver would recognize that these are two disconnected problems and would, well, solve both of them taken together in a time no longer than requiring the one or the other. But it turns out that general purpose ILP solvers, refined as they are, do not understand about this structure in the problem. So when you see an instance like this, it helps to really cut the graph in two pieces and pass this to the solver, and then separately, call the solver again with the second part of the input. And it turns out that this is much faster than calling it on this graph with two connected components. And this is what you see sketched here in figure 2. So you have two graphs, they look intertwined, but actually you see no binary factor between the two components. So you can simply call the solver on part 1 and then call the solver on part 2. So this is one way of helping a generic solver. Another way of helping a generic solver is to recognize such trailing trees, because when you have a tree, actually for a tree in a factor graph, you can do inference very, very efficiently using dynamic programming. So you start passing messages from the leaf nodes of those trees, and the result of such a message passing on trees is globally optimal. So this is very, very cheap, and again results in a factor that is modified with respect to the original factor. And this new factor now encodes all there is to know about the right-hand side. Again, generic ILP solvers don't understand this, and you can help them by solving, or by rolling back these trailing trees. And here you see a couple of runtimes. Here we have now images which are 32 by 32 up to 2K by 2K. So this is quite realistic for a decently resolved image. And then you see that the normal ILP solver already for with today's computers hits the 10-minute barrier at sizes like this. And now if you use the first trick that I showed of partitioning disjunct parts, then you hit the 10-minute barrier only for much larger images. And if you take all tricks that I've mentioned together, then you actually get this graph here. And note, of course, that the scale here is exponential. Yeah, so you wouldn't, if I extrapolate linearly, you wouldn't want to spend years, waiting for your ILP solver, provided it doesn't run out of memory, which it will do before that. So there are ways of helping your generic ILP solver. There's one caveat, namely the plot up there was for a multi-label problem, and there, the end of what was possible was at 50 by 50, And this time we look at just binary problems. So it's not a, it's not quite a fair comparison, but still the message is if you have such a generic solver, you can help it to solve realistically sized problems. Of course, these are tricks. So if you defined a problem, or if you designed it in a mean way, then it could happen that QPBO only finds the labels at very isolated instances. So for example, if it had not found the label at this vertex here, if QPBO had not found the label at this vertex, then I would, delete the blue dot here. And if it had not found that label either, the whole thing would still have been connected, and we couldn't have partitioned it into two parts. But that said, the graphs on which Jörg worked here were generated randomly, so they were not designed so as to be particularly easy. Yeah, so these you can call them heuristics, but they work very well even on random graphs, which are even harder than the graphs that you have in normal computer vision. Okay, I have much to say about the structure of such interlinear programs, but I will not manage in the -2 minutes that I have officially. So I will have to continue with this next time. Sorry about not having managed today. So there's really interesting stuff ahead next week, because we will talk about the structure of these interlinear programs and what we can learn from them. So how they can be approximated or relaxed, and how you can obtain not quite perfect, but very good local optima in a fraction of the time that you would need for finding the globally optimal solution. So interesting stuff ahead. See you next week.